Good way to start, right?
Okay.
So, yeah, so, well,
First day back from break.
yeah, I know. Tough day, right?
I think you might need to calibrate that.
Oh, thank you. Somebody must have moved my board. I hope they didn't mess it up because it was working real well. It's just not liking the... yeah, happy Monday, right?
It's Tuesday.
Happy Tuesday. Happy Make-Believe Monday. Okay. So, with these guys, you just have to realize that your matrices were equal. So, if one is fitting right on top of the other. So, are we okay with finding the missing values? Okay. And this can only happen on an equal one. This piece is equal to 5. Set it equal to 5 and solve for x. This piece equal to 12. This piece equal to 4. It looks a little strange like this. You can't put this in your matrix, obviously, but you can set them equal to each other and solve. Then we just had two matrices. Now remember, they have to be congruent. They have to be same dimensions, 2 by 2, 2 by 2, for you to add them and subtract them. You can do a scalar multiply on anything, but you have to have the same dimensions to add and subtract. It has to be a 1-for-1 relationship. Everybody good with this? Okay. You stop me if you're not good or if you can't remember what we did. Okay, again, this is same dimensions. They have to be the same. For you to add or subtract. Multiply of a scalar, you can do any of them. This is your scalar multiplication, 3a. Right. Okay. This one again. A little bit annoying, but you kind of get the pattern of how to do this. And 19 is not the same dimensions, so you could not add or subtract them, but you could multiply by a scalar. But then when it got to this subtraction, you couldn't do that. And just say not possible.
Oh, I put undefined.
Undefined, not possible. No solution. Just don't give me zeros in the matrix or leave it blank. So you just had to multiply a by 3, b by 2, and subtract them. This one, multiply x solve for x. You have to solve for x in this guy first. Multiply a by 3, and then subtract b minus a. The one thing you want to be careful of is the direction that you go in. And don't forget the 1/2. You want to make sure you go in this direction, b minus 3a. We've been doing the a minus b, so just make sure you go in the right direction, and then take 1/2 of your results. Easier to keep them in a fraction than it is a decimal. The decimals take a lot more room in your matrix, and sometimes then you have to scroll to see the rest. Just flip it, math, enter, flip it back to a fraction. Okay. These were just a couple of them seeing if you could multiply. Remember, when we look at the dimensions, you want to make sure the middle two are the same. Okay, we have 3 rows, 2 columns, and 3 rows, 3 columns. These have to be the same, but you can't multiply them. You could even try them in your calculator. It's going to give you an undefined solution. These okay? These worked? That means this is your resulting matrix. Let's just walk through this multiply, because that's probably the only one that might be troubling to remember. Remember when you multiplied, you're going to multiply this whole row for this column, then this column. So, and you can multiply in your head, I get it, but the only problem is you won't see if you were off on your pattern. So I always multiply it out so that you could see that it's the same pattern all the way through. These will follow the same. You'll be able to spot these guys. You'll be able to spot it across, -1, 6, -4, 5. You can see it right from your matrix. If you're comfortable with the routine, just multiply. You don't have to show it out. In other words, skip to this part right here. That's fine. And you're resulting in a 2 by 2. So even if you forget where to cut this off, if these have 4 in here and you need 2 positions, divide it by 2. Every 2 is going to add together. And check it on your calculator. This is the one thing, though, we need you to be able to do by hand, is the multiply. The add, the scalar multiply, you can pretty much use your calculator. Because I wouldn't be able to tell if you didn't. But this we need you to multiply these all the way up. You okay with these? Again, 3 by 3. So you're going to be resulting in a 3 by 3. And again, if you do it out this way, if you're struggling with it, write them out. You can definitely see where you're off. If I made a mistake here, or wherever I make a mistake, and I notice that it's not matching up, I say, whoops, I must have put a 7 instead of a 0. Sometimes you're doing it fast in your head, and once you go back, you're not going to be able to catch that mistake. You can narrow it down. If you do it on your calculator and you see what area it is, just go back to that row, column, do that part again. We're good? Everybody remembers the multiply? That's probably the hardest part on this. Okay. As weird as that looks, it matches up, and we end up with a 2 by 4. Is that the last? That was the last one, right?
Yeah.
Any questions up to now? And we're saying that just like when you multiply any 3 numbers, it doesn't matter what order you multiply your matrix in. So if you're multiplying A times B times C, associative property says you can multiply these first, or you can multiply these first. You're still going to get the same result. Remember, when you multiply them, the only thing you have to check for is to make sure that you're lined up. Your things are lined up. Distributive property, same thing for your regular distributive property. If you're going to add these 2 and then multiply by C, you can distribute this and multiply it that way. Most of these, guys, you're going to be doing on your calculator anyway. So you won't really notice that difference. Just so that we just hit a couple of these. And your scalar multiplication probably works the easiest. If I do, it doesn't matter if I do 3 times A times B, or if I do 3 times A times B. As long as these are lining up again when you multiply. So nothing really serious here, and most of it you'll kind of spot while you go through. This is more like get comfortable with doing your matrix. Sometimes you see a matrix equation like this, and a lot of books like to subscript. These are just subscripts for X. These are 3 elements, and they just subscript element 1, element 2, element 3. So sometimes you'll see these kind of separated. They take, and we'll do one in a second. They take all your coefficients out. They take your constant out. This is the equal to, -4, equal to 4, equal to 2. And then they find your solution. Technically, when you find your solution, if you took this times this, it would equal B. So it's just another way that you'll see these written out, and you'll solve them. You don't have to change this equation to solve for x, because you're going to do this here. You're going to separate your matrices. Well, sometimes you'll see this. You'll see in a book, they'll say, solve this matrix equation. And what they're asking you to do is you'll see it when we do a system in a minute. They'll separate that system into, like this would say 1x minus 2y plus 1z equals -4. Y plus 2z equals 4. 2x plus 3y minus 2z equals 2. So we're separating these into the coefficients, the constant, the equal thing. We're going to find your solution. You know when you do RREF and you get those little solutions at the end? They're just subscripting them. Technically, you're getting 3 solutions in there. Where we say x, y, and z, they're just subscripting them, x1, x2, x3. And I can't call them all x because there'll be 3 different things. We see this sometimes, not a lot, but sometimes. So what we're talking about here is you're going to have your 3 equations, or however many you have, and you're going to separate them into your coefficient and your constant. And I don't think this showed up. Okay, so you're going to separate your coefficients. There's your coefficient, there's your constant, and your answer is going to be in this sense. You're going to get 3 variables. So instead of saying x, y, and z, you're subscripting x1, x2, x3. Your x1 is your x, your x2 is your y, your x3 is your z. But instead of them calling it this way, they're going to just call it subscript. Remember when you see the little numbers down here, they're have you used subscripts before? In chemistry? Yeah, like a lot of the things we use, you see through, and physics will use it again too. Anybody have physics? Do you use subscripting in physics? No? It's just another way to look at this. Instead of calling it 3 variables, they say, well, you really only have one solution, x equals.
So that's the answer?
Well, we didn't find the answer yet. We're going to solve this, but we're just going to put this into this format. So our answer is going to say x1 equals, x2 equals, x3 equals.
Okay.
It's just another way of subscripting rather than calling it x, y, and z. It has because basically it fits this format. And at the end, it's kind of cool because once you put it into that format, if you actually multiply a times x, it does equal b. So it's a good way to check that everything worked okay. This is another way to check. It's another way to look at a matrix. We really don't do a lot with them in here, but we expose you to a lot of ways that you can use them. And chemistry probably uses matrix. If you take this in college, especially like balancing equations and stuff, you'll probably put it in a matrix somehow. A matrix is really powerful. We don't do a whole lot. We do solving systems, we do determinants, and we do a couple of other little things, Kramer's rules. We do a couple of things just to expose you, but when you actually work with these, they're pretty powerful. So all we're going to do is set this up with an RREF. So we're going to set this up and pull all these out. We're going to put your constants here. And we're going to do an RREF. Remember how we put this in your matrix and then we did RREF? And your RREF should return. Remember how it looks? This is the way you can tell. Right across. There's your diagonal with the ones. And then your solution is here. So we're just going to take this out, and this is going to be what x is equal to. This is your x1, which is your x. This is your x2, which is your y. This is your x3, which is your z. If we took this column that we found, and we multiplied it by a, it would give us B. Just another way to solve a matrix. What else can I get here? One more thing. I want to add one more thing. Everybody okay with this? We didn't really do a whole lot different. We just subscripted through your X. Rather than say X, Y, and Z. You're still getting the same answer, but we're not saying X, Y, Z. We're saying subscript this, and it matches this equation. It just sets this up in a different format. And you'll see different problems call for different formats.
So can we just leave it in that, like, with the 1, 0, 0, 1, 0?
No, you're going to give me this. If we ask for this format, you're going to give me this.
So just X equals...
X, and then put your numbers here. And this is your answer. This is your answer.
Okay.
That's it. And it's the same process. It's the same thing we've been doing. It's just another way to look at it. Some books you're going to see always set that up into AX equals B.
I just wanted to make sure I was
Mm-hmm. This book that we use, I don't know if you look at it that often, it only makes a short reference to it, but everything else we solve regular. It doesn't really dwell on that either, but just so that we expose you and you know what we're looking at. Determine whether you can do these. So again, the key part here is follow your order of operations. You can multiply any matrix by a scalar. That's not going to give you a problem, right? That's going to end up in the same format that C is. So what you're looking at is B, which is a 2 by 3. And you're going to subtract, whether you add or subtract, they have to be the same format. You're going to subtract whatever C is, a 3 by 2. So are they set up the same? No. So therefore, this is not possible. This is undefined, not possible to do. So that's all that this is asking. B times C. I'll show you 1 second. Like if this was a 2 by 3, your answer would say you can do it, and you would result in a 2 by 3.
Oh.
Mostly it's the multiply. B is your 2 by 3. C is your 3 by 2. So can we multiply these guys together? So what's our resulting matrix? 2 by 2. Because these have to match in the middle, and the resulting is the 2 on the outside. C times B, you're going to do this first. So C is a 3 by 2, and B is a 2 by 3. So do these line up? So this guy would result in a 3 by 3. And whether you add or subtract, they need to be the same. So D is a 2 by 2. Can we do that? Can we take a 3 by 3 and add or subtract a 2 by 2? No. So this is not possible.
Can you explain the first one again?
This one?
Because you just had a bunch of them there and I didn't understand like where they came from.
Okay. So we look at order of operations. We say the first thing we want to do is multiply this matrix C by 3. So it doesn't matter what matrix your wood looks like. You can multiply by any scalar number, and it doesn't change it, right? Say I have a matrix that does this. 1, 0, 1. Can I multiply every term by 3? Every element by 3? And I still get the same result, right? So when we multiply anything by a scalar, we're okay. Then we go to subtract. Subtract says they have to be the same dimension, because we have to go element to element. It's like placing it right on top of each other. But when I look at B is a 2 by 3. When I look at C is a 3 by 2. They don't match up. This would have to be 3 by 2, or this would have to be 2 by 3. Go again.
If it says BC times C, can you do that?
Where are you?
It said BC.
If it said BC, so let's see what BC says. BC says, let's rewrite it so we don't confuse anybody. B is a 2 by 3, and C is a 3 by 2. So what would your resulting matrix be? And you would also subtract or add a 2 by 2? Absolutely.
So it doesn't matter, like, if it's that.
But what did you do here? Is this associative property? When you switch this order, it's commutative property. And multiplication doesn't work with commutative property, but associative, you're just changing your parentheses, and that would be fine. But you can't do commutative property. So that's a good example of commutative property doesn't work. Associative, yes, but not commutative. Okay. So this guy, B times C, and we can probably see it in this one. 2 times 3, I don't know if this one works or not, I don't have the answer. B is a 2 by 3, and what is C? C is a 3 by 2. So can we multiply those?
Yeah.
And we end up with what? 2 by 2. And what's D? 2 by 2. Can we multiply those?
Yep.
And what's our result? 2 by 2. Okay, let's change this. Let's change this for the associative property. So instead, let's do this. Let's see if that associative property really works. So C is a 3 by 2. D is a 2 by 2. So far, so good. And what will my result be? 3 by 2. And B is a 2 by 3. So can I do that? Yep. So does the associative property work? Yep. The associative property does, but not the commutative property. So it's just another way to just see that it works. Good. When in doubt, you can always put it in your calculator and try. And if it doesn't line up, it's going to tell you error. I think it says invalid dimension or something mismatch. It'll say something like mismatch or something about your dimension. So you can always try it. And if they give you something like that, just make up a matrix. You can just make up a matrix. And then this last guy, you guys try the last one. It works from ordered operations. And if we did this one out, we could show that the distributive property works for this. So does it work? What's your result? What's dimension? 2 by 3. You got 2 by 3? Okay, so this guy, B is a 2 by 3, and C is a 3 by 2. what will that result be? 2 by 2. Can we subtract a 2 by 2? Yep, and we will result in a 2 by 2. And A is a 2 by 3. So what's your result? 2 by 3. Just follow order of operations, just like you normally would. There's one other thing that I wanted to show you. It's not on here, but and your worksheet is there. You don't have to use your book. This is perfect. Sometimes after you do RREF and you get your results, you know, normally your matrix says this. It's got this line here. And then your results are all here. Sometimes what happens is it doesn't work. Because you remember when we solved your systems of equations? Sometimes we had no solution. Sometimes we had all solutions. So how would you tell when you do RREF? So, for instance, if you got this, this is where my X, my Y, and my Z should be. I should see this guy right here, this one, should have a 1 here, but it doesn't. There's all zeros there. This means I have infinite solutions. And we have another way that we can say infinite solutions because of our matrix. So remember, it would be like when you're solving those things and you join 2 and you join 2 more and you came to like 6 equals 6 or 4 equals 4. And you say infinite solutions. We have another way to say this infinite solutions. We would start with your Z, and we would say, let Z equal A. And A is any integer. Right. Now, we're going to backtrack and solve everything in terms of A. So the second one says, this is your X, so it says Y minus Z equals 0. So all you're going to do is back substitute. You're going to substitute your A into here. Solve for Y. And Y is equal to A. You're going to back substitute again. This says X, and there's no Y, plus 3Z equals 1. You're just going to substitute. You're going to substitute A into here. And you're going to solve for X. So X is equal to 1 minus 3A. And that's the best we can leave for a solution. If you switch this around, negative 3A plus 1, it doesn't matter. So you've got everything solved in terms of A, where A is any integer. So if I plugged a 1 in here, this would be a 1, this would be a 1, this would be 1 times 3 is 3, minus 1, this would be a negative 2. You'd get your solutions, because infinite solutions means you have more than one solution. But when we did your systems of equations, all we could do when we got down to that other part, like 6 equals 6, 2 equals 2, we would say all solutions. If 2 equals 6, we'd say no solution. But for an infinite solution, we have a way of defining it. I'm not sure if you have one on your homework that's going to turn out like that. So just kind of keep track of it in case it does.